재밌어? Oh, wonderful. I expected some troublesome, annoying headache question, but looks like you're okay. Good job. Very nice. Great. As you know, our exam is available on Blackboard. So that's okay. Any questions before we start? No? So simply exam start from now. When is it due?
Wednesday.
Wednesday before class, huh? Wednesday. So 1 week is given. There are 7 questions, as I mentioned before. 7 questions. If you listen to me and practice 2 to 3 hours per day, it will be very easy. Page no. If you didn't what happened, the exam will be difficult. It's time intensive, time consuming. So what should we do if it's time intensive and time consuming?
Start now.
Start now, I like it. Start now, even. Start now. At least start today, please. One rule, as you know, and must follow rule. One rule. And can anyone tell us what is the must follow one rule?
Don't collaborate.
Huh?
Don't collaborate.
Don't collaborate, of course. It's exam serious. It's exam serious. Why I do take home exam? Because I trust you guys. I trust you guys. You will do by yourself. Do alone. Exam as much as you can. Do by yourself as much as you can. And make some notes. If you have some questions after the exam is over, we can discuss. No problem. But from now until you submit next Wednesday for class, do not discuss with anyone. You just do by yourself. Do you agree? Do you promise? Yes. Please take it serious. Grade sometimes is important, but not that important compared to your honest and integrity. So, from my opinion, grade is important, but not as important as your integrity and honesty. Just to do as much as you can and submit, and let's see what happens. As I mentioned, if you practice every day, 2 to 3 hours, it will be very easy. But that's what I asked you first class. If you didn't know what happened, well, now you got 1 week. 1 week for how many hours? You still have a lot of hours. Time. Look, okay, military service. During my military service, we had it's called typhoon training. Typhoon training. So we have a lot of other training, but the training name is typhoon training. What do we do? Simply. Simply, you carry your bag, everything, including your blanket, your equipment, your gun and bullet, everything. It's about 25 to 30 kilograms weight. So 25 to 30 kilograms is about 60 pounds weight bag. We carry the bag and we walk 100 kilometers. 100 kilometers, about a little more than 60 miles. How long? 40 hours, almost 2 days, but it took about 40 hours. What do we do? It's called typhoon training. 40 hours, walking 100 kilometers. What do we do? They are very mean. They let us walk 10 minutes and then 10-minute break. And then walk another 10 minutes, and then 10-minute break. Who has done any military service? Nobody? At the first moment, 10-minute break, what a sweet, amazing, very good. But you walk without sleep, we don't sleep for 40 hours. I'm not lying or I'm not joking. We had more difficult training for 1 week, but this is name is for typhoon training. You keep walking 24 hours, 25 hours without sleep, So this type of training, the objective is to improve, increase, or strengthen your mental strength. So you keep work 24 hours, 30 hours. I don't want to take a break anymore. Why? You sit down, take a break, try to sleep a little bit. You don't want to wake up anymore. But we must wake up and we must keep going, keep walking to the destination. Then if you will be left, they just leave you off. But anyway, nobody is staying behind. So what I mean, we got 1 week to submit. Okay? 1 week is long time, so if you haven't worked hard so far, next 1 week do your best. I guess you still have time to do well. Yes? Any questions? Still, learn in the morning. Don't sleep over. Learn in the morning. Okay? Since several of you came late, come on, guys. I really don't like what's going on. Don't be late. You don't learn from me. Have I ever late? Have I ever been late? Not easy. Being late is easy. Easiest one. Being late is easiest one. Don't push your easiest way. Not being late, not easy. It sounds easy, but not easy. Have you tried not to be late ever? Not easy. No, really not easy. Being late is easy. Well, everybody can do it. Anyway, one rule must follow rule. Do by yourself, simply, because it's really serious. And we have integrity rule, honesty rule. Universal method follow. Do by yourself as much as you can and submit before class, October 1st, next Wednesday before class. Okay, let's begin quickly. Question 1. Now we have done the homework. So if you did homework well, it's so easy. Okay, we are looking for properties. As you can see, what properties? Density, conductivity, heat capacity, viscosity, enthalpy of these three mixtures. If I give you some hint, please answer using this given unit. So little pay attention to those unit. Unit is given. So answer here with this given unit. I just check your number, and then if you are wrong, of course, negative point. If I give you more information, if you define property set, it will be easy. Question number 2, what do you think? Question number 2 we have done in the class. Anyone? What the question number 2 we must use? Neil? I think we have to use design spec, but first, what template should we use? Or what model should we use? Electrolyte. Wonderful. So you can use electrolyte. But if you look at those units, looks like you can use electrolyte in English unit, and then Neil says design spec. Maybe you can do local design spec. This one has this, for example, this sweet H2O. Ammonia concentration should be 5 ppm, and the condenser temperature should be 170 degrees Fahrenheit. So maybe we can do 2 separate design spec in maybe local design spec. Why local design spec? You know why? No? Because we only have 1 unit block, so you can do local design spec. If you have many unit blocks connected, then you must use global design spec. That's the difference. So why? Global design spec will affect every unit block. So local design spec only affect that 1 unit block. That's local and global. Okay? So we have only 1 unit block. We can do a local design spec. Question number 3. Now we have done in class. So if you practice, you are already done this question number 3. Who practiced already this one? Okay, Chase, great. Sean, a little bit. Anyone else? What are you doing, guys? Too busy? Okay, I know, everybody's busy. But we have done the class time. Let's see, Chase, can you explain us a little bit or what this one is looking for?
Trying to maximize. Oh, can you go back to the top?
Mm-hmm.
Using that equation in Fortran, I believe that's what it's called,
Mm-hmm.
to estimate the profit, pretty much,
Okay.
using operational cost and cost of equipment, all that stuff.
Okay. During class time, Chase responded correct. Chase, can you explain us what we are looking for in this question?
You're trying to minimize cost with the diameter that you use.
Okay. Simply, we are looking for the optimal inside diameter of piping system by minimizing the total cost by using the equation here. So simply Chase and Chase, thank you. Okay, for information. Chase said maybe we can use Fortran because equation is given. Where do you can define the equation? Simply use Fortran. Okay, but this question is looking for what will be the optimal inside the diameter of this pipe to reduce the total or minimize this total cost by using this given equation. That's the logic. Yes? Okay. And if you look at your attached screenshot, means more than one. Okay, I don't know how many, maybe define tab, input folder, result tab, result folder, and the optimization folder means you have to attach two screenshots in. Just attach it really carefully every question, and then attach if I have to attach. If you don't, I will assume you didn't do. Lucia, if I assume you didn't do this question, what happens?
Negative one.
Negative? Fine, okay. I am very strict on grading, so don't expect to be generous for me. I am very strict. Why? Why I am strict? What do you think? Really, why I am strict on grading?
Because you give us a week to do it, and so we should be able to do it right.
Because I believe you guys are very smart at this. Hopefully you understand. My English expression is not that good. But from my opinion, University of Arkansas, you are in here, my standard is high. Okay? You are here, my standard is high, and I expect much more than this. Okay? I have received on your grade. Attach screenshot of aspect simulation showing the final total cost. Where can you find out that the final total cost in aspect? If you concentrate where during class time is easy. If you didn't, little look around, especially the navigation thing. Just little look around, you can find out. Question number 4. Design refrigeration cycle. We did power generation cycle and refrigeration cycle. This one is asking for design a refrigeration cycle using isobutane or isobutane. Use SRK property method. So method is already given, just use it. Okay? Determine the vapor pressure at this temperature. Determine the vapor pressure at this temperature. You can use those pressure at that temperature. Use those pressure to design refrigeration cycle. Now, question is determine the amount of isobutane necessary to extract 1 gigajoule per hour of heat in the evaporator. Maybe you can do design spec to find out how much isobutane is necessary to extract 1 gigajoule per hour of heat in the evaporator. And present the main flow sheet with flags of temperature. So in the main flow sheet, temperature should have 2 decimal points. pressure should have 4 decimal points, and the vapor pressure should have 2 decimal points. Just read carefully, go step by step. Question number 5, as I promised, that's your homework you submit today. Okay? You have done 2 sensitivity analysis, but in this exam, and then please use this documentation. Do not use any other documentation. So numbers are changing. And so just follow this documentation available on Blackboard because I changed those numbers. But anyway, in this question, I ask you exactly same concept but use optimization instead of 2 sensitivity analysis. We had 2 sensitivity analysis. Now you can carry out 1 optimization. So you combine that 2 sensitivity analysis idea or concept into 1 optimization, and the same thing. Attach the screenshot of very tab in the optimization folder and attach the result, screenshot of optimization result, same as shown in figure below. This final values filled in means your initial value will be like that. In final value, we have question marks. You fill in here and look at the unity. In this case, looks like the mole flow of methanol. So I use the mole flow. So please pay attention to the unit and then design in Aspen. Okay, easy. Little additional, we have done pretty constraint, but in this case, I ask you to design 2 constraints. Okay? The first constraint is, okay, from sensitivity analysis or optimization, we found out the optimal temperature pressure of the reactor. Okay? But if you look at the constraint, the highest pressure should be 40 bar because the reactor designed up to 40 bar, even though the answer might be the highest pressure will produce the most methanol. So we got the constraint. We have to constrain the reactor pressure up to 40 bar, and CO2 concentration should be greater than or equal to 10%. Set these 2 constraints, and then carry out the optimization. When you do use Aspen, you will understand better what I'm talking about. Question number 6, we have done very Monday, so we can pass. Okay. Question number 7, okay. A binary liquid stream, in this case, benzene and toluene. Okay, so benzene toluene mixture. Okay. Our target is to separate this mixture so that we can get benzene 99.9% and toluene 99.9%. Simply. But not many information is given. Not much information is given. How can we design to get very pure benzene and toluene from top stream, bottom stream respectively? Follow this description where I ask you to set up. First, to use these 2 columns. As I said, these 2 columns is shortcut distillation column. So first, use these 2 columns with initial reflux ratio of 5, and then find out initial specification, design specifications. For example, number of stages, I think. So you get those information from these 2 columns. Then use the information to design layer column. So we are designing 2 different distillation columns where we can use duplicate to facilitate into stream. And then what is that? We need to find out purity, benzene purity, toluene purity. Maybe we can do design spec again. 2 different design specs. Now attach summary screenshot. Okay, and then report the optimal column design. Okay, number of stages, feed stage, molar reflux ratio, distillate to feed ratio. Please fill out the blank. Should I give you a little more information?
Yes.
Yeah. Okay. Why not? Look, why not? If you use shortcut these 2 columns, the result you can get is you will get some minimum number of stages and actual number of stages. So let's say minimum number of stages is 16, actual number of stages is 19. Then means you can little manipulate, play around the number of stages from 16, 17, 18, 19, and then see reflux ratio and then purity. And then think about to describe the rationale why you selected the optimal. We are looking for optimal column design specification. But so you fill out this blank, and then I ask you describe the rationale why you selected those optimal column design specification. For example, if I choose 19 stages, okay, as I mentioned, 19 stages and then reflux ratio about 7 compared to if I choose 17 stages, reflux ratio will be 30. You have to think a little economically. 19 stages compared to 17 stages, and the reflux ratio 7 compared to 30. Maybe the column size we have to design a different size. So your description, maybe you can adapt to some economical point of view. Even though we didn't do any economic analysis, you can at least make some description based on performance, efficiency, and economics. Yes? Since I am a very nice guy, I will show you one question. Tell me which question? Question number 7. Raise your hand. Question number 7. Let's go democracy. Or love. Okay. So simply question number 7 ready? All right. Let's look at it. Okay. I explained, so let's look at it. Binary liquid stream containing 50 mole percent benzene and toluene, which enters the distillation column at 50 degrees Celsius 1 bar, while flowing at a rate of 1000 kilomole per hour, is to be distilled, distillate and bottom slip. Use NRTM method. Okay. There are no pressure drops. Okay. And this one operates at 1 bar. Your goal is to select the optimal number of stages, feed stage molar reflux ratio, and distillate to feed ratio to get the mole fraction of top product and bottom product both at 0.999 means 99.9% purity. All right, let's go. So if I go new chemical reaction, so I have benzene, toluene, okay, and it says what? NRTL property method. Estimate missing parameters. Okay, table generation completed. Yes. Let's go here. What I mean, okay, we are going to use one duplicate, and we are designing distillation column. So as you can see, this is a shortcut. This is called shortcut distillation column. So let's first try to use this two column to get some basic idea to find out input specifications for rigorous, robust red cup distillation column. Okay. So I'll name it P, DE. I'll name it P1. This to 2 column. Let's say this to 2 top. This to 2 bottom. Okay. Let's go next. Celsius and 1 bar and 1000 kilomole per hour, but 50%, so 500 kilomole per hour. 500 kilomole per hour. I go faster so that you can copy. Now, initial reflux ratio is given. So here 5, okay? And condenser, reboiler, no pressure drops, maybe 1 bar. Now here, light heat, benzene is lighter, and then our target is 99.9%. So toluene is heavier, maybe 0.001%. Run the simulation. Okay, we are looking for mole fraction. Right, 99.9 goes to mole. Let's see, mole fraction. So I will check the mole fraction. And what I'm saying, you get some idea. So if you use shortcut these two column, this top stream should be benzene 99.9%. Bottom stream, toluene 99.9%. So we get the requirement. Okay. But what we are looking for, we are looking for some basic information. So if you look at here, okay, minimum reflux ratio 1.3 is possible, but actual reflux ratio we used to 5. Okay. But we are looking for the optimal number of stages and reflux ratio and feed stage variables. We vary those variables and find out the optimally. Now, minimum number of stages is 16, number of actual stages is 19, feed stage is 10. We are going to use that information, okay, to design rigorous, robust lead fractal. That's what we are doing. Two, that's the column, top, yes. Let's go. Now, let's choose what number of stage you want to choose. Big page.
If you have a higher reflux ratio, wouldn't that be negative? Like you wouldn't want a super high reflux ratio because then that would mean that you're having less product. Because it's like return over distillate. So you want a lower reflux ratio or higher one?
What do you think?
I think we would want a lower one.
I think so. Higher reflux ratio means you return to column more, but of course higher reflux ratio may produce more pure component, pure product. That's why we increase the reflux ratio. You return more to distillation column, maybe you can produce purer product. That's the reason we increase reflux ratio. Right? But you increase reflux ratio means you have to design very large size of column because you return to column more. Yes? Now, same thing. If we increase number of stages, we can get purer product. Same thing. But as I mentioned, these trays are very expensive to install. If we want to increase number of trays, we have to build that column height was very tall. So it's related to cost to me. Okay? But the basic concept is yes, we want to keep as low as possible reflux ratio, as low as possible number of stages. As long as we can meet the purity, 99.9%. Okay, anyway, what number of stages we choose?
16.
Let's try 16 plus 3. Okay? Condenser is total condenser. Reflux ratio is given already. It was 5, so we can use that one. Now we are looking for also distillate to feed ratio. Now we don't know distillate to feed ratio. Maybe we can start this one any number, 0.5, and then we can do design spec later because we are designing. But what will be the optimal distillate to feed ratio? 1 will be optimal. In Aspen, even though you get like 1.1, which is not theoretically possible, if you do mass balance, I put 1. If 1 come out, it's already optimal. But if 1.1 come out means some reaction happen in the column, which is usually not. Okay, so distillate to feed ratio, the optimal value will be close to 1, 0.995, 0.9991. But we don't know. So let's start with 0.5. And then, because we choose distillate to feed ratio, this is feed, this is a distillate. Alright. We chose 16. As you know, the number of feed stage also affect the result. Usually, the feed stream about middle, so 8 or 9 around 8, 9, 10, 7 to 10 around there. Just it doesn't matter. Just check. Okay. Number of stage 16, I can choose 8 or 9 either one. Will be max optimal. But you just try. Try. It doesn't matter. It doesn't take much time. See. Alright, now let's look at our summary. So we are looking for this one 99.9%, this one 99.9%, this one 99.8%, this one is 66.6%. Idea, right? We got some idea. But we got no warning, no error. But this one should be 99.9 and this one should be 99.9. What can you do to achieve that goal?
Increase number of stages.
Okay, increase number of stages, or you can do increase of number of stages. So it says 19, something like that. Then stream maybe 10. Okay, let's try. So let's see. Hopefully I don't get any warning error. Okay, no warning, no error. Then look at here. And where is mass fraction? Mole fraction. This one? What's going on? Do you see more fraction somewhere? Huh? Oh, here, okay. So, you got 166.7%. We didn't meet our requirement. So, what else then? Increase reflux ratio, okay. We can do those things manually, but I'm looking for why we do manually. We have to use some tools. We have learned those tools to use. What tools? Tool design specification. Okay. During your homework, we have done enough sensitivity analysis. So during exam, I ask you more design spec and optimization to master it. That's what we have learned. Let's keep practicing. Okay. We have unit block, so maybe I can use red frog design spec here. Okay. So simply, what we are looking for, optimal reflux ratio. So first, we can choose more purity because we have to meet the requirement. Target is 99.9%. Let's try. Component, engine should be 99.9%, toluene should be 99.9%. Okay. First, let's try to change the reflux ratio we are looking for. So reflux ratio, I don't know, maybe 1 to 100 or 50. Let's try to look at it. Okay. So if you look at here, check every time. So this one should be 99.9%, 99.9, 99.9. But toluene is not. But so far we found a benzene purity, and then if you go Veritab result here, that's what I asked you to insert in. Looks like about 3.3 reflux ratio. We got benzene purity, but not toluene purity. We can do another design spec. What can we do this time? We can find out more purity of toluene this time. Okay, so let's try to do toluene this time. It's the bottom stream. And I can set up another vary. In this case, we vary distillate to feed ratio. I used the gassing number 0.5. but maybe we can find out 0.001 up to 1. If you put here like 2, Aspen will still calculate it, but it's not theoretically possible for mass balance. So if I do, oh my quickly, I could not believe this. I expect some errors. I don't have any errors. What's going on? You envy me? You envy me? It's from all hard work, I see. No sweat, no sweat. No sweat, no sweat. So, red circles, this value is in. So I got 99.9%. What we are looking for? We are looking for reflux ratio of result. Now you need to put this one in. Do I need to show you? Print the screen. Go to print, Control V. Cut this part. Control C. And then attach it. Where is this question is looking for? Attach the result summary scheme, no. Optimal curve, no. Attach summary result here. Something like that, eh? Yes, please. And let's look at it. This rate feed ratio, simply the final value is 1. Optimal condition. Now, if you know we used 19 number of stages, can we choose maybe 16? Because these two distillation column, minimum number of stages can be 15.6 something, maybe we can choose 16. Okay, now then 16, the feed maybe 8. Let's try. So remember, when we chose 19, the reflux ratio was 7.2, and then this feed ratio was 1. If we choose 16, let's see what happens. Oh, we got error finally. Yes? That means what? Maybe this design is not a good design. Can I choose 17? It doesn't take much time. 17 maybe, a little higher is better. Be the same, so 9, 10. Oh, no warning, no error. Make sure. All 99.9%, okay, 99.9%, sure. If you check, now we get reflux ratio 35.9. I got no warning for error. The simulation should work first thing. So make sure the simulation works first. Now if you look at the reflux ratio is 36, and still this rate feed ratio try to make 1 because it's optimal. And as I said, you can attach this one and then put red circles and submit. Any questions? How nice I am. I showed you how many questions I already showed you. Do you want me to show you another question? Oh my goodness! At least you guys, we don't have time, eh? I wish I could do that, so we have time.
We can stay late.
I think that's enough. Too nice also no good. You are here to learn it, not here to graduate. Don't think to graduate. Think about why you are here.
You probably already talked about this, but how do you know if you take specialty chemical or chemical when setting up?
So, okay, no problem. If you go, for example, go to me. No, that's for new. So when you go, if you click this one, there is here preview already. You can look at this preview. So what's the difference if you use chemical with metric unit? Preview, you can see degree Celsius bar kilogram per hour. Specialty chemical is metric unit, not much different, but little bit different. For example, use ATM instead of bar.
So it's just a unit thing?
Just a unit. Any other questions? No questions. I like it. From Friday, we start chapter 7, our textbook. Textbook available on Blackboard. Yes? Did you know textbook is available on Blackboard? Just print out chapter 7, chapter 8, chapter 9, chapter 10, appendix A, appendix B. Those are we are going to use from now on, next 5 weeks or so. Right? And then exam 2 will be in class exam 50 minutes. You have to practice a lot to finish exam 2 in class in 15 minutes. You will be running out of time. So what that means, now exam 1 is a take-home exam. You got 1 week. Everybody will do very well. So the final grade will more depend on the exam 2 score. So make sure your exam 2 score, make sure you get very high, enough grade to get an A. Yes? Olivia, what do you need to do to get very good grade? Practice a lot.
And do good on exam
Exam 2, Natalia.
I need to study a lot.
Study a lot. I'm asking if I'm looking for some other answer. Really?
Start early?
Start with I like it. Oh, every I like it. I'm looking for something else. Come on.
What's the question?
Oh, don't worry. Right. No.
Computer class.
Come on, that's not good. That's easy.
That's what I
Computer class is easy. Come on.
Read the textbook.
Of course we have to read the textbook. But something else I'm looking for. Come on.
Take notes.
2 to 3 hours a day.
2 to 3 hours a day. How can you define you study hard or work hard? How can you define? The standard is different to everyone. Somebody 1 hour is already I worked hard, like page think 1 hour is enough. So the standard is different, so I give you very specific number. 2 to 3 hours a day. Every day. You, same thing, you don't do now and then you accumulate, you want to later on exam point. If you don't start today, you want to next week, simply you cannot finish it. I tell you. Anyway, next 5 weeks or so, what we learn, we simply learn engineering economic analysis, very interesting topic and very good topic from my opinion. How much money it takes to build a new chemical process or plant? In other words, definition, capital cost. So we will learn in chapter 7 and appendix A, okay, to estimate capital cost. How much money it takes to build a new chemical process or plant? Capital cost. How much money it takes to operate chemical plant or process is called operating cost. In other words, cost of manufacturing. In chapter 8, we will learn cost of manufacturing. How to select the best process from competing alternatives. If you have many choices, alternatives, how can we select the best practice or process? Using the concept of time value of money in chapter 9 and chapter 10. How to combine the capital cost and operating cost, provide process profitability, and then we'll do risk and uncertainty analysis in chapter 7. So, from Friday, bring your textbook in. Just print out our textbook. The hard copy is this, very expensive. But luckily, we have the PDF file available. So at least print out chapter 7, appendix A on Friday. Yes, bring the textbook in. Chapter 7, appendix A. So that we can learn chapter 7 from Friday. Since we are early, let me ask you, close your, don't use your devices for online or internet. Maybe you can prepare one sketch paper. You don't need to write down name, so you don't have to worry about. Prepare one sketch paper.
Does someone have an extra piece of paper?
Jacob. Wow, amazing. Only Jacob is missing. Isn't it wonderful? It's a test. It's a test. So you don't need to write down names, so you can write down anything. Yeah, don't worry. You don't need to write down names. You can write down anything. No problem. Okay. We have learned MATLAB. Oh, MATLAB. You know MATLAB? Huh? MATLAB. What does MATLAB stand for? Math library. Math library. MATLAB. Don't look at device, man. Just answer. What's the MATLAB stand for? What does MATLAB stand for? Huh? Matrix, I like it. Matrix laboratory. I like it. Matrix. Matrix laboratory. Laboratory. LAB or RAQ or something like that. And that's what the matrix is. Matrix laboratory. We learned the Fortran. What does Fortran stand for? Huh? Oh, we learned Fortran. We use Fortran. What does Fortran stand for? Function training something. Formula translation. Formula translation. That's the Fortran. This is warming up. We just warmed up. What we have learned? Write down. What does ASPEN stand for? No, we have learned ASPEN for 5 weeks, so you should know. What does ASPEN stand for? Write down and submit, and then you can leave. You don't need to write down names, so you can write down anything. A stands for agriculture, right? Aerospace, maybe? Huh? S is science, society, science, simulation, I don't know. A is agricultural. Absolutely not it. But anyway, write down anything, submit, and then you can leave.
I'm not telling. No, I don't know.